Hello everyone, welcome back to my channel. I am Arushta, graduating in Venkateshwara College of Engineering, Bengaluru. I am belong to second sem. Today's subject is physics and topic is about Lorentz field and classes MOSSOTTI equation. Introduction about Lorentz field. The realm of electromagnetism, understanding the behavior of materials subjected to electric fields is paramount. The Lorentz field and the Classes-Mossotti equation are two crucial concepts that shed light on this phenomena. In this comprehensive discussion, we deal into the intricacies of these concepts, their significance, derivations, applications, and relevance in contemporary scientific inquiry. Understanding the Lorentz field. The Lorentz force, named after the Dutch physicist Hendrik Lorentz, describes a force experienced by a charged particle when subjected to the both electric and magnetic fields. Mathematically, it is expressed F is equals to Q into E plus V into B, where F stands for Lorentz force, Q stands for charge of particle, E stands for electric field, V stands for velocity vector of the particle, and B stands for magnetic field. This equation illustrates how to charge particle moves in response to electric and magnetic fields, experiencing a force perpendicular to both the velocity vector and magnetic field lines. In a dielectric material, such as an insulator, the presence of an electric field polarizes the material, aligning its constituent charges. This alignment results in an induced dipole moment within the material, leading to the net electric polarization. Mathematically, the polarization P of the material is related to the electric field E by the equation P is equal to epsilon naught Xc into E, where epsilon naught is vacuum permittivity, Xc is electric susceptibility of material. This equation highlights the relation between the electric field and induced polarization. Derivation of Classes-Mossotti equation. The Classes-Mossotti equation provides a deeper insight into the relationship between the polarization of a material and its dielectric properties. It establishes a connection between the electric susceptibility of a material and its molecular structure. The derivation of Mossotti equation begins with considering a dielectric material composed of polarizable molecules. When subjected to an external electric field, these molecules experience a torque that tends to align their dipole moments with the field. This alignment leads to an induced polarization within the material. Assuming an isotropic distribution of polarizable molecules, we can define the polarizability. Alpha is a single molecule as a proportionality constant between induced dipole moment P and the applied electric field E. P is equal to alpha E. The total dipole moment per unit volume P of the material is given by the product of the number density of molecules N, and the dipole moment per molecule P is equation P is equal to NP. Substituting the expression for P, we get P is equal to N alpha E. Now we consider the relationship between the polarizability alpha and the dielectric constant epsilon of the material. The dielectric constant epsilon is defined as the ratio of the permittivity of material epsilon to the vacuum permittivity epsilon naught. Epsilon is equals to epsilon naught divided by epsilon naught is equal to epsilon naught, where epsilon r is the relative permittivity of the dielectric constant of the material. In terms of dielectric constant epsilon, the electric susceptibility can be expressed Xe is equal to epsilon minus 1. Since the electric susceptibility is related to the polarizability alpha through the polarization E, P is equal to epsilon naught C into E. We have P is equal to epsilon naught into epsilon minus 1 into E. Substituting epsilon is equal to epsilon r and rearranging, we obtain P by E is equal to epsilon naught into E r minus 1. Comparing the expression with P is equal to N alpha E, we find N alpha is equal to epsilon naught into epsilon r minus 1. Finally, by substituting the expression for alpha in terms of polarizability per unit volume alpha V, we arrive at Clausius-Mossotti equation. AV divided by 3 is equal to epsilon naught into epsilon r minus 1. This equation relates the polarizability per unit volume alpha V of material to its relative permittivity epsilon r and provides a fundamental connection between the microscopic properties of a material and its macroscopic dielectric behavior. There are some application and significance for the Clausius-Mossotti equation. Thank you. Thank you all for watching my video. Please like and share.